let's have a look at two other really important number systems, the octal and the hex number systems within computing. So octal is our base 8 number system, all right? What does that mean? We're going to use the digits 0 through 7 when we represent octal numbers. Let's have a look. 4762 base 8. You will notice what I've done is I've put the 8 down there so we can see we're talking base 8. We've got 1, 2, 3, 4 digits. So 1, 2, 3, 4. But as we've done with 2 to the power of 0, 10 to the power of 0, we start here with 8 to the power of 0, 8 to the power of 1, 8 to the power of... So I think you're starting to see, I'm hoping, that pattern. And we go again. 8 to the power of 0 is 1, 8 to the 1 is 8, 8 squared is 64, 8 cubed is 512. Easy. All right, now we're going to, as we've done before, take those and pop them in there. So the 4, okay, the 7, the 6, and the 2. So we do 4 lots of 512. That's what we've got here, 4 lots of 512. We've got 7 lots of 64, 6 lots of 8, and 2 lots of 1. We add them all together and we end up with the magic 2,546, which you're starting to see the pattern there. It's the same number we did previously. So 4762 base 8 is the same as 2546 base 10. Let's take it to the next level, converting decimal to octal. We're going to use the quotient remainder method, just as we've done before. Divide by 8 and we record the remainder, and then we use the quotient to divide again. 2546, okay, 2546 divided by 8 is 318, remainder 2. So we've got our 2. 318 divided by 8 is 39, remainder 6. Our 6 gets moved across. Okay, 39 divided by 8 equals 4, remainder 7. Brilliant. And then 4 divided by 8 equals 0, remainder 4. And we bring our 4 in, and we've got our solution. Straightforward. Now, this is a really important numbering system when it comes to, within Unix, for file permissions. Okay? And we've got those up. We need to convert binary to octal, group the binary number in sets of 3, because I disappeared, from right to left, and then we convert each group to the octal digit. What are we talking about? So, binary, 000, okay, is 0 in octal. 001 is 1, so you can see our octal numbers on the left, and then our binary version of those octal numbers there. Now, file permissions allows us to know, or tells us what we can do, or what the system can do with a file. Can it execute it? Can it read it? Can it write to it? What can it do? So, what? Our binary number. Okay, so we've got our binary number, we've got our octal number, and now what we're going to do is we're going to group it. Okay, so as I said, we group it into sets of 3 from right to left. Okay, so like this. Okay, got it? And then what are we going to do? Well, we're going to have a look now at this number, which is what I want to do. 342, so that looks like 342,391 base 10. We're going to convert to binary. Are we ready? So this is our binary number. Already done it for you. Then we're going to group like this. Okay? So we're converting, remember we're converting this to octal. I've got the feeling some of you may have lost us. Okay, so this was, let's change color here. This was our binary, okay, in groups of 3 because we're taking it to octal. Remember? Okay, and 1 0 1 0 0, we come down here from our chart, and in octal that is 4. 1 1 1, okay, is 7. 1 1 0 was our 6, which comes up here. 0 1 0 is our 2, and that goes up there. So that was how we did that conversion. We have this number as a base 10. I converted it already to binary, and now we're going to convert it to octal. So we take the 3 digits. Remember how we did that? We've filled all of those in there, and then we've gone 111 is the 7, and we've popped that in, and we've repeated that pattern. Okay? And we ended up with 1 2 3 4 5 6 7. Base 8. So 342,391 base 10 is equal to 1 2 3 4 5 6 7 base 8. I realise that's a lot to take in, but it's important that we're getting that, okay? So let's now take a look at hexadecimal, which is even more fun because it's base 16. So we're using the digits 0 through F. What? 0 1 2 3 4 5 6 7 8 9 A B C D E F. That's how we do it. 9F2 base 16. How are we going to do this? This is how we've done it. Okay? Same way we had, let's get my pen up. Okay? We had 3 digits. So we needed our 3 digits. And I've seem to have made that mistake in a few places. That is 16 to the 0. In the notes that will be unlined, it'll be 16 to the 0. Okay, so 9F2. So, well, we had 16 to the 0 is 1, 16 to the 1 is 1, 16 squared is 256. So our 9 comes down here, our F goes in there, and our 2 in there. And when we convert it, we have 9 times 256, 16, or F times 16, and 2 lots of 1, which equals 2,546 base 10. Now, if you're unsure about that, if we look back up here, 9, 10, 11, 12, 13, 14, 15. Okay, so that's how we got this to be that. And when we added them all together, it came out exactly how we anticipated it would. Let's have another or a bit more of a conversation about this. So hexadecimal is almost always used to display memory within computers. We've got our digits, we've got hex, okay, hexadecimal. So hexadecimal and binary work together very closely. All right, and hexadecimal and binary work together very closely. Yes, I meant to say hexadecimal to binary listed together. Sorry, I'll leave that in for you. So hex 0, there we go, and 1, and you can see the whole way across. They're our hex numbers, and then the binary, because we set it up in that manner. Let's now convert hex to binary. Okay, so we're going to group our binary numbers in sets of 4, all right? And we say from right to left, and then we convert each group to the hex digit. This is our number, 22965667350 base 10, and there it is in binary. So let's convert this binary number to hex. We take our 4 digits starting right to left, 1, 2, 3, 4, so though they go there, and we repeat this the whole way along. Now, if we came down to the furthest left and we don't have enough digits, then we pad with zeros, but we put those all the way across. And 1110 is E. 1101 is D. So this was the way we converted hex to binary. In one sense, very simple. It has the same steps. And that's what I'm hoping you've seen through this process of number conversions. They are these sets of steps that we repeat over and over and over, which means it's a simple thing once we know how to code, but it's a really simple thing to actually create and write our own converters for this.